So after this short view on Bamberg, it's my pleasure to welcome you all to the first session of this day. And it's a particular pleasure for me to welcome Tony Cohn as a keynote speaker to this conference. All of you surely know him for one or more of his many activities or research papers. This makes it pretty hard to introduce Tony Cohn briefly, but adequately. Tony Cohn is professor of automated reasoning at the University of Leeds, and he served in many ways the AI community, including editor duties for journals such as Spatial Cognition and Computation or Artificial Intelligence. And he has been chairman, president of ISB, Your AI, KR Inc., and the ICHKAI Board of Trustees. So he is recipient of the 2015 ICHKAI Donald E. Walker Distinguished Service Award and the 2012 AAAI Distinguished Service Award. But of course, we also know Tony Cohn for his seminal works on qualitative spatial temporal representation and reasoning, or recent works in the areas such as cognitive vision, robotics, grounding language and vision, and the decision support system. Among his works, one stands out: the development of the RCC theory and the region connection calculus. So he's one of the C's, and you may figure out which yourself. His 1992 KR paper has almost 3,000 citations by today, which roughly estimates to or translates to every third day a scientific article being published that cites this work ever since it was published. So it comes as no surprise that this paper received this year's Classic Paper Award as part of the Test of Time Awards at KR. And I'm pretty sure that the following presentation will become just as memorable for KI. So Tony, thanks for accepting our invitation. The screen is yours.
Well, thank you very much indeed for that very kind introduction, and indeed for the honor of inviting me to give this talk. Let me just share my screen. Right, well, as I say, thanks again for this invitation. I was very much looking forward to visiting Bamberg in person. I'm sorry we have to do it this way, but I'm still very pleased to be talking to you today. So today I'm going to be talking about three main topics in decreasing order of time. So I'm going to spend most of the time on natural language acquisition and grounding, which Diedrich already referred to in the introduction, and then a little bit of other work towards the end on manipulation, robotic manipulation, which I'm getting more and more involved in at the moment. The first of which involves quality spatial representations as well. So moving on from that, talking about that first topic, the grounding language division. So this is a work done by a student of mine, Mohamed Al-Amari. It got published in AAAI 3 years ago, and there's a journal version under review at the moment. So what we wanted to do was to design and implement a system that's capable of incrementally, and that's very important, bootstrapping its knowledge in vision, natural language, and their connection, starting with very little information beforehand. And that's so that's what we were trying to do. This came out of the Strands project, which is a big EU project with 6 partners across Europe. And as part of that, we were trying to learn about events. And this wasn't in the original project, but we sort of came up with this approach, these ideas, because we were trying to find a way of annotating events in video without actually explicitly pointing to where they were. And so we wanted to use natural language to do that. And this kind of work I'm going to talk about today grew out of that. So the three main conditions learn concurrently and incrementally the visual representation. So we don't assume any prior knowledge about the visual concepts, the language grounding, and also we don't assume any prior knowledge about the grammar. It's just a string of words in some language which this machine has to learn. We've also created a number of open access data sets or extended them, and the software is available open source on GitHub. So this is just an overview of the architecture. I'm not going to have the time to talk about everything today, so I'm going to concentrate on the yellow boxes. So just going along the top row, we have video clips, relatively short, maybe 1 or 2 minutes maximum, of some action or small number of actions being performed. either in a synthetic environment you see here or in real life environments. And we then use standard off-the-shelf techniques, which I'm not going to talk about today, to detect any people in the scene, detect objects and track them. So what I'm going to start talking about today will be, first of all, learning about the visual concepts, both simple visual concepts, such as faces, colors, spatial relations, positions, objects, etc., and also complex visual concepts, such as activities, either performed by humans or robots. And then we have language, which we have annotations feature those video clips, and from those we extract n-grams in this work, which either take 1, 2, or 3 grams, and from then those n-grams become possible linguistic concepts, which we might or might not then get successfully grounded to some of those visual concepts learned in the top row. And so we propose possible hypotheses there in step 3 there, and then we tend to overgenerate at that point. So then we do go through a couple of filtering stages, one with some rules to get rid of some very obvious misgenerations, and then a step where we do this sort of mental simulation to validate the hypothesis further. And then I'm going to very briefly talk at the end about just learning probabilistic context-free grammar rules from that, without going into the details of the vision trees or the robot control language trees that are used to actually match up the sentences with the intermediate representation, which I'll be talking about. So this work was evaluated on 4 data sets, a new one which we created at Leeds, this Leeds robotic data set, which you can see is a Baxter there. It's hand manipulated by somebody with a joystick, and then we performed various tasks, and then we had various annotators describe what was going on there. And you can see actions, you can see properties of objects, you can see spatial relationships, you can see positions, things like top right corner, and so forth. Then there was a trained robots data set, was originally created, not by us, but for a competition, Semival 13. We then extended that, not only by adding the Arabic translations of the Amazon Turk annotations, but also by the original data set just had an initial position and a final position. We then animated that automatically into a video. Thirdly, we used a data set from University of Austin, Texas, which is relatively simple, but just gave us another third-party data set to evaluate our work on. And then finally, a data set which involved the robot now was observing the human rather than actually doing anything itself, and it's the humans that are doing the actions. And again, this was a data set created as part of the STRAND project. And the robot that was doing the observation is the one you see here, which we call Lucy. Okay, so those are the data sets. So in order to learn the simple visual concepts, it's relatively straightforward, but remember we want to do this incrementally. So what we do is we estimate incremental Gaussian mixture models at each stage as we process each video. And so for faces, we do this over eigenfaces. Over for colors, we do this over HSV space, the HS part of HSV space. And then for shapes, we use this FPFH representation. It could be something else. We're not. It's the method that seemed to work quite well. But you know, if your favorite shape representation could be substituted instead. Further simple visual concepts are spatial concepts. So things like tabletop locations, and you can see here the kind of clusters which we get out for example, top left, top right, and middle bottom. We estimate and again an IGM over tabletop relative directions. So for every pair of objects in the scene, we look at their relative directions, and we take we take the relative angles in 3D space, so including azimuth as well. And finally, we take the pairs of distances between all pairs of objects. And again, those form a potential space. So these are continuous spaces, and then what we do as a result of clustering is to then cluster these continuous spaces into a finite number as determined by the Bayesian information criterion of discrete concepts. For the complex concepts, we have two types. We have the robot actions, and in the fourth data set, the kitchen data set, we have human actions. So these are temporally extended observations, and we use for the robot actions, I'll introduce in a couple of slides' time this graph-based relational representation for actions. I'm not going to say much about the human actions. You can read more about that in the paper last year by my other student, Paul Duckworth, in the AI journal. But basically, we use this this other code web-based topic modeling approach. So here, this graph-based activity representations, if anybody is familiar with some of our previous work on learning activities from video, you'll know that we've been using this three-layer graph of where we have temporal relationships at the top layer, spatial relationships in the middle layer, and objects at the bottom layer. Here we have used a slightly different representation. We eliminate the temporal relationships, as here we assume that the world consists just of a sequence of states, where within each state we have the spatial representation is constant, and all the properties are constant. And then when we go from one state to another state, when one of those properties changes to a different value, to a different cluster in the appropriate visual space, which we've just learned in the previous slides. So here you can see, just to illustrate that, we have got here the robot hand approaching an apple. Here we have a relation node between the hand and the object. There's a couple of different relationships we can have, either direction relationships or distance relationships. The hand is a special object which kind of the robot inevitably knows about already, so that just has a location. But the unknown objects here, which in this case is an apple, but the system doesn't know about that yet, it doesn't know it's called an apple, and that has the various properties we talked about in the different visual spaces we talked about in the previous slides, so color, location, shape. And these nodes then get instantiated with particular clusters from the different visual spaces. And we go from one state to another when one of these things changes value. So here, in this state here, the hand is moving, but it's continuously approaching. The distance is always changing, but the direction is staying the same. And then when we go to this state, then the distance between the two objects stays constant, so it's not changing anymore. But the apple starts moving. It's changing its location. So that enables us to segment the continuous world into this finite number of states. Here's another view on the same thing. Here's a slightly more longer sequence where we've got the hand approaching the apple and then picking it up and moving it away. And you can see that as we go from state to state, something changes. So going from state 1 to state 2, the hand location changes from location 1 to location 2. Going to state 3, the hand is now closed, and the distance goes to D1, from D1 to D2, and finally moving to state 4. Locations of the hand and apple are both L1 rather than L2. So in order to generate candidate concepts for the groundings, those n-grams, we basically take these relational graphs and we take not all subsets of those graphs, but sort of very structured subsets of those state graphs that you just saw a moment ago. So you see these objects here. These are sort of the graphnets for the objects and their properties. Various either it's in one property or possibly pairs of properties or triples of properties. And then we also have the relations here. So something could be either an n-gram could be grounded to a distance concept or direction concept, and then states, verbs in general will get grounded to these actions, which are state-to-state transformations. Of course, the system doesn't know which words are colors, which ones are shapes, which are locations, which are verbs or relations yet, that's part of what it's going to learn through the grounding process. So here we're going to connect the individual n-grams from, place the apple in the bowl, and there's a set of n-grams here, and we need to figure out that the system needs to figure out that apple refers to this particular shape, apple, rather than any of the other shapes or the directions or colors or anything. And we're going to use integer linear programming to make these associations. We're going to allow multi-multi associations. So by multi-multi, I mean that one word could potentially refer to two different concepts. So for example, orange could be both a shape and a color. And also one concept could be referred to by two different words. So a particular color might perhaps be referred to by both cyan and sky blue. So in order to connect language to vision, we're going to tentatively associate n-grams with these graphlets, and then we're going to filter and validate these associations. And then, having learned to correct associations, we're going to then learn the grammar. And when I keep on saying then, it implies like there's sort of really three-step phases to this. But in fact, remember, we're doing this because we don't keep any of the videos. We're doing all of this step by step, video by video. And for each video, we're going to be doing all of these steps. So in order to try to figure out which n-grams correspond to which visual concepts, we build this correlation matrix, which I'll call K. The rows here are the n-grams, and the columns are the visual concepts. And U1 up to UU. And we've got the rows, n-grams labeled delta 1 up to delta B. And you can see I've sort of colored these in the different shades of gray. And so this is sort of this matrix after we've done some calculation of how strong the correlation is. And this is a matrix which gets updated every time we see a video. We keep the original, but then every time we see a video, we process it, and we then figure out which are the correct associations. So the next phase, big thing to do is to try to convert those gray values into either black or white, make a definite decision about whether a particular n-gram refers to a particular visual concept or not. And so the way we do that, as I say, is with this interlinear programming, where we're trying to max. That's the next slide. So first of all, how to calculate those gray values, those correlation strengths. So we take the number of times lambda delta nu that each of the concepts are being observed together, occurring in the same video, and divide that by the number of times that the concepts are being conserved individually. And then we take the max of those two. And then we multiply that by this term on the right, which basically penalizes the probability of concepts which have only been observed a few times, because we don't want to give too much strength to those observations yet. And so this value K would predictor cell would be 1 if they always seem to be appearing together, and 0 if they never seem together in the same pair of inputs. And then the interlinear programming, we then take this maximization of this sum. So K is the value we just talked about in the previous slide, and A, this term A is either going to be 1 or 0. And we then choose to make it either 1 or 0 in order to maximize this sum. Subject to a couple of constraints. The first constraint keeps the groundings relatively sparse, and the second constraint insists that we have at least 1 n-gram for every visual concept. Now that does tend to overgenerate, because it may well be that there are some visual concepts which that we haven't had any language described yet, but those will get filtered out in the subsequent stages. And as I say, doing this using interlinear programming allows these multi-multi associations. So doing that then converts the original correlation matrix we had on the left into the one on the right, where we've got rid of the intermediate gray values and things are either now white or black. There's either an association made between the two, the n-gram and the visual concept, or not. You can see that there's still, well, there's a few things to note here. One is that things like function words correctly don't get any visual concepts associated with them, at least not in our representation. There's no visual representation for the. We also have some words, n-grams here, which actually have two possible concepts here. We can see that up might be this action, but probably it's just this direction. And similarly, apple, the system hasn't yet decided whether it's which one of these two shapes it is. So in order to try to eliminate some of these incorrect associations is what we're going to look at next. So first of all, we have these sort of 4 simple rules which allow us to filter some of those incorrect associations using case analysis. So what this is doing is looking at the graphlets for the 1 grams and 2 grams. So we look at the graphlets associated with concept A, B, and A and B.
Huh?
Hello, yes? Somebody saying something? No? Okay. We look to see whether those graphlets are the same or not. And if they're all the same, then we just choose the association for the bigram and throw away the ones for the individual 1 grams. If the graphlet for the bigram is the same as one of the 1 grams but not the other, then we keep both the 1 gram representations, and if they're all different, then we keep everything. And so that then converts the previous correlation matrix now to this one, where we've now managed to realize that its pickup is the correct language to describe this particular action here, rather than pick or up. We've got rid of red and apple because the system's realized that essentially red and apple are 2 different concepts. The language is compositional, so we don't need to learn a representation for red apple separately to a representation for red and apple. And again, it has the red is not, we don't need to learn that. All we need is red. But we still have this ambiguity about what apple means. So that's what we're going to look at in the next slide. So here I mentioned that we could do this validation by mental simulation. So the idea is we've got one video, we've thrown all the previous ones away, but we've got the current video we're processing. And we don't do this at the very beginning, but once we've processed a few videos and we've got a reasonable strength of strong associations, then we compare the current video, we look to see what graph that generates, and we compare that with the hypothesis graphs we get by connecting the meanings of the words together, and we look to see which ones are correct. So just to make that a bit clearer, let's look at this example. So suppose we've got a particular video where the hand is picking up an apple. So we've got pick up the apple. So we already said turns out to be a function word, so there's no graph representation for that. Pick up has already been determined to be an action, and so we've got this 4-state representation of pickup, and then apple, and that's unique. But apple has got 2 possible groundings. It could be this shape, or it could be this shape. We don't know yet. So we're going to use this mental simulation to figure out which one's correct. So if we instantiate this with this version of apple, then we get this complete representation of the sentence. And if we instantiate it with the mug, we get this representation. Then we look to see from the actual video what the actual, we just look at the visual concepts, ignoring the language, look to see what representation we get from that. And we see we get this one where the concept is grounded to the apple rather than the mug, and so that's the correct one. And so we're able to correctly learn that apple represents shape S1 rather than shape S2. So I'm going to skip over fairly quickly a bit about learning grammar rules. So the idea is we're going to learn a probabilistic context-free grammar. We start with an empty PCFG. Once we've generated these descriptions and learned associations, then we can build a tree from those, and this is what we call a robot control language tree, and then we can associate. Looking at the terminals here, we can learn that there's in our grammar we'll go on to have a rule which says that an action could be a pickup, a function word can be the, and a mobile object can be an object, which can be a shape, which can be an apple. And initially, assuming this is the very first rule we ever learn, the probabilities of all these things will be 1. But as we learn further actions, for example, if we learn another action put down, then the probability here will change not to be not 1, but maybe 0.5 or 0.6 or something. And that's similarly for the other, as we learn further shapes and further different objects and so forth. So just briefly run you through a little bit of the evaluation we did on this system. We compared our system against a supervised system. So obviously we don't expect to be doing as well as the supervised system, which has access to the ground truth. In this bar chart here, the odd numbered bars refer to our system, and the even numbered bars refer to the supervised SVM-based system. So you can see that we're not doing as well as the SVM-based system, but in many cases we're not doing too badly at all, and not that much less. In some cases, we're even here. You can see actually we do slightly better than the SVM. So this is just evaluating the visual concepts, not looking at the language at all, but just seeing whether the associations, the clusters that we create correctly correspond to the clusters created by the labeled ground truth. Here are some of the examples of some of the clusters we learnt. For example, in the lead robotic data set, you can see the colors being clustered to there. Here, the different shapes, balls and cup mugs, and you can see that it's done that pretty well. The spatial locations here, we don't have a name for yet this, but this is obviously top right, and this is something like bottom middle. And the distances again nicely clustered into nice peaks here. So we then look at the grounding, looking at F1 scores for those, again, comparing this against a supervised system. In this case, we use an HMM-based supervised system. Again, we don't expect to do as well. But yes, many times we do pretty well. So for example, here, looking at the grounding of colors, that's really pretty good. And the grounding of objects is pretty good in the trained robots data set. So again, I'm not going to go through this in detail, but you can see that in general, we're not doing too badly at all. And again, remember, there's actually no prior knowledge being provided here. Just the fact there is a perceptual space for vision, for color, there is a perceptual space for shape and so forth, but the system has to learn everything else from scratch. And in this incremental based method where it can't just do this batch mode and try to optimize across all videos. And then these are body data set. Here's some of the groundings. You can see sometimes we get things wrong. Now looking at the actual examples, you can see this is actually not a completely stupid grounding quite. For it, I guess we didn't have enough, at this point of learning, we didn't have enough non-white balls. Looking at the next one here, and the kitchen data set, you can see that some of the mistakes are understandable. For example, here, Alex almost always wore glasses, but in our computer vision system wasn't able to, all it could do was recognize faces. It couldn't recognize glasses, so we don't have a perceptual space for objects on people's faces or anywhere else on their body. So there's no way it could ever ground glasses correctly. And we only represented just tops and the bottoms of bodies, so there was no way of correctly learning genes. We were only looking at colors for those. But you can see in general, and again, sheet is the kind of, you can see how that might get confused with copier and printer, since that would frequently co-occur. Having done that, we can then describe, we can get a brand new video, we can try to describe what's going on. Here's an example from the kitchen data set, and you can see it just describing the colors of the upper and lower garments and the particular action that's been learned. And when the person turns to face the camera, then is able to name the person, as you'll see in a moment. There we are, Mehmet. Okay, we can also use the language, the grammar we've learned to actually, rather than using this the test template based description, we could actually use that to describe it, to use the grammar then to generate sentences. I said we also had Arabic, so annotations for one of the data sets. So this is just showing how it works on the second language. This is again the grounding, so comparing it against the supervised HMM system. The first two are for the first two columns are for the Arabic, the second two for English, so you can see how it compares. In general, the English does slightly better, and that's because Arabic has two genders, Of course, German has 3, which would make it even harder. And these words then have different, so where you will then change the endings on certain words depending on the gender, for example, verbs. And this means then that there are essentially more words. And because we don't have any inbuilt notion of gender built into the system, it actually has to learn the female and male versions in the grounding separately. This is just showing you how incremental learning takes place as we process more and more of the data set. And you can see in general, we start off with some level of performance, and then it is getting basically monotonically better over time, except for this kitchen data set where we seem to have a little bit of a dip around about the 60% mark for shapes and locations, but it soon recovers them. I'm not quite sure why that happened. You can also see that, although we have, if you were to store the raw data, we'd be using a huge amount of space here. But if we're just storing because we don't store the raw data, we only keep a video, process it, and then throw it away, we're only needing to store about 10 to the 4 bytes. We're evaluating the grammar. We came up with 139 grammar rules for the Ronix data set. That's the Baxter one. 533 for English, and because of the gender issue, rather more for Arabic. In terms of how well we parsed commands, novel commands, and the robotics commands data set, we did pretty well, about 87%, a bit less well in the extended trained robots data set, that's the synthetic data set. And one reason for that is that there were various concepts in that which we don't yet have a representation for. So for example, there are things like aggregate nouns like stack and row, column and group, and we don't have a way of we don't have a perceptual space in just what I talked about so far today to do that. In fact, I have had some students recently who have built perceptual spaces for aggregate objects and are now able to learn groundings for aggregate nouns such as stack and row. So here's an example of it parsing a novel sentence: move the blue egg at the top left corner to the right of the red mug, and you can generate a parse tree for that, and using the grammar on the right. And you can see, I mean, this might not quite be the grammar and parse that you generate if this is a human generated grammar, but it looks reasonable. We've got an action here. We've got this noun phrase here, a spatial relation here, which then refers to a particular noun phrase here. And I said already given there's values there. So in summary, we're able to take in raw vision, unparsed words, categorize n-grams, learn discretization of continuous feature spaces. We're able to create multi-language groundings, validated by method simulations using digital programming, and use of probabilistic grammar, learn all this incrementally. We've tested this on 4 domains. Okay, so let me my remaining minutes, just let me briefly talk about the robotics work on manipulation, which I wanted to talk about. So both these were bits of work were motivated by the problem of manipulation in cluttered environments, like trying to get something from the back of your fridge. And sometimes maybe you can just lift it straight out, but sometimes you might have to move things to the side, as you see there on the top right. So rather than working with the real complexity of that in our initial work, we've worked with simpler domain, this tabletop domain, with various different kinds of blocks. And so this is some work which appeared in ICRA earlier this year. And the question is then can we reach directly, or do we perhaps we should move objects out of the way first? If we're going to reach, which path we're going to take, and if we're going to push objects, in which objects are we going to push, and in which direction? And so we look at existing state-of-the-art robot planners. Typically, these are stochastic planners. They're based on random sampling and configuration space. As the number of objects increases, it gets very high dimensional. And these, particularly as you get these very high dimensional instances, then you tend to get very long planning times. And we were sort of trying to find a solution to avoid that. So the idea was, could we learn from humans? But rather than doing the standard sort of learning from demonstration where we just do individual instances for the robot and maybe moving the robot arm, what we're going to do is to get the humans to manipulate it in VR, in virtual reality, and then use that as training for our robot manipulation planner. So we have, this is kind of the overview of our human-like planner. We take these VR demonstrations. We then segment these demonstrations into a kind of high-level representation, which I'll mention in a moment. Then we learn decision classifiers for each of the main things, like which object to choose, which gap to go through, which and so forth. And then having learned those, we can then use those in an actual new instance, a test scene, where we then extract the features and apply our algorithm. And then having generated a high-level plan, we then use a standard low-level controller, stochastic planner, but that's now got the guidance of where to go rather than just blindly trying to try all possibilities. So let's look at the VR data to begin with. So here we've got, you can see there's somebody here manipulating is this video going to play? No. Don't know why the video, so it was playing fine when I tested it earlier. Anyhow, you see this virtual arm here, and well, I don't know why it's not playing. Oh, here we are. It should have played automatically. So you can see we've got sensors attached to the elbow, the shoulder, and the hand, and they've got a little button on the controller there, which they can use then to move objects and retrieve the target object. So this is our training data. And then the next stage is to segment these demonstrations. So what we do is, in that segmentation, we identify gaps, we look for segments which connect gaps, and then for objects, we have to decide which direction they're going to be moved. So we have a qualitative representation of space. So we have front left, front right, left right, back left, back, and back right. And then we're going to learn classifiers which choose one of those qualitative directions to move to. And so, again, here we yes. So here you see one of those plans now, just represented with a sort of stick-like arm, and you can see the plan being instantiated here. And then at the bottom left of this slide, it briefly popped up the high-level plan, which the system, which the hand actually produced for this case. So the high-level plan was go through gap G2 and then move object 6 to the bottom left. So that's essentially what we get as the training instances. And so this high-level plan is a sequence of key points in the action spaces connected by segments. So with that, we learn decision classifiers for each of these things we have to decide about, which gap to go through, which object to choose. If we're going to move an object, which direction we're going to move it to, and which segments do we then go through. So we use lots of qualitative spatial relations here, and we train binary classifiers for each object, because of course we don't know how many objects we're actually going to have in any scene. So we can't just say, well, there's 3 objects or there's 3 gaps, and let's just choose whether we always should go through gap 1, 2, or 3. What we want to learn is for a particular gap, how good is that gap? And so we'll essentially learn a probabilistic classifier, and then we'll then end up choosing the gap with the highest classification probability. So having done that, train the classifiers, we then can actually apply the human-like planning algorithm to the environment. So we apply the classifiers. We then, having got the classifiers, we can then connect the different gaps together, which is the segments. We create segments. We then estimate the arm configuration, check expected collision, produce the high-level plan, which you saw a couple of slides ago, and then give the system that high-level plan to the low-level controller. So in looking at in the robot simulation world, we get a pretty high success rate on the examples we tried, 94% compared to the 84% success rate on the stochastic planner without our high-level plans guiding it. And you can also see the planning time was much reduced, 1.56 seconds over this, rather than 17 seconds. We're using the geophysics engine to do this. We also did experiments with a real robot. And you can see here, we've got the human-like planner on the left, and it's realized there's a huge gap off to the right there, and it's going to go through that gap to retrieve the object. Whilst the stochastic planner, its default plan is to go for a straight line, and it tries to find the minimum, the fastest plan from that. And this is the one it's found, and you can see it ended up much slower. So that was for a 7-object situation. Here's one for 9 objects. So here, the system, why it's playing so slowly today. There we go. So again, this system, it accidentally touched that one block, but basically it's found a nice gap to go through to reach the object, rather than trying to push objects out of the way as the stochastic planner does. And then finally, here's an 11-object version where there's quite a bit of work to be done in terms of moving. Even for the human-like planner, there's no gaps to go through. This, I really don't know why these videos are so slow in playing. Here we go. So, and notice these, in this case, we didn't have the objects arranged in nice neat rows as we had in the training data. They're still approximately rows, but it was able to convert those objects into sort of virtual rows, and then still find a good path through to the target object, and much faster than stochastic planner. Okay, so learning from humans to interactive VR. We had this semi-qualitative, semi-quantitative representation of task space. We have this high-level planning algorithm, and this seems to scale reasonably well. And although we've got this particular UR5 arm there, it's clearly applicable to other robot morphologies. So just very quickly, I've just got other future work trying to go for even more non-row structured environments. We've already been experimenting successfully with inductive logic programming rather than the SVM-based classification method, which we've used in the published paper, and to move to more closed loop planning. So just very briefly, in my final couple of slides, just talking about, there's another piece of work done by another student at Leeds, Rafael Papalas, which is going to be published in KI2020 later on in the autumn, and also simultaneously in Robotics Automation Letters. And here, rather than getting the human help in advance, we get human hints at runtime. So the idea is the system plans in simulation mode, optimizing trajectory. If the planner fails to find a solution after fixed time, then it asks for human help. And the human then, the human help just consists of selecting an object and the direction of motion for it to be moved to. So it's very quick and easy. You just click on an object and then just drag the mouse in a particular direction. And that's all you have to do. You don't have to plan the complete path. And then the planner then incorporates that hint as an update to its cost function in its trajectory optimization, which I'm not going to go through in detail here. And it then re-optimizes and hopefully finds a solution this time. So, and the idea, of course, if you just had a single operator and just one robot, that would be rather inefficient use of the human, because why doesn't the human just manipulate the robot directly? The idea here is that we're in some sort of factory setting where you've got many robots doing things, and you can have a single operator supervising multiple robots. So here you can sort of see a whole bunch of robots, one per row, and then most of the time, maybe this top robot R1 manages without any human help, but the second 2 robots listed at some point, they need human help. And for the robot, the human comes along, and then you can see with this white arrow here, selects an object and gives a direction of motion to move it to, and then the plan is able to complete successfully. And so here's then just a video showing that in real life, with the video is going to play. Okay, it should have played automatically. Let me play it manually. And so you can see there's the human is controlling 6 robots here, and when we focus here on one of them, you can see the white arrows again, the human providing. And again, you can see there's a pretty complex situations with many objects. Okay, so that's all I have time for. Really, here's just some statistics showing how well that works. You can see that it has many fewer failures, only 13 rather than 34 in the autonomous case. Optimization time was faster. It only took 5 seconds for all of those 50 videos, so only about a second on average per video. And you can see the total time taken by all those 50 instances was less as well. Okay, so thank you very much for listening, and acknowledgements to the various financial sponsors of the work, and I'll take any questions.
Thank you very much for the interesting talk.